So you want to write a renderer in one of those fancy schmancy new graphics APIs like Vulkan or DirectX 12, but all this sync stuff is way too hard. Well, there are some ways to remedy this. We have virtual command buffers, we can just deal with it, or we can use a render graph, which will be the topic of this video. So what exactly is a render graph? A render graph is a way we can represent the order in which render passes are drawn in a directed acyclic graph. You can see how this would be useful for a modern graphics API like Vulkan or DirectX 12. These graphics APIs, unlike OpenGL, expose much more of the work the GPU is doing, requiring you to sync your own resources. But why do we even do sync in the first place? That's because the GPU is meant to chug through as many operations as possible. Due to this, it focuses on being highly parallelizable, as in it can run in a bunch of threads. Just like in a CPU multi-threaded application, things execute in an arbitrary order, and we need a mutex to lock and stop stuff from happening before it should. Think of a pipeline barrier as a sort of mutex. Since all commands submitted to the GPU can run in arbitrary order, we don't want things happening before a resource is initialized or written to. So how do we even implement this render graph thing? Before we even think about writing a render graph, we should know what render passes are. Now, I personally use dynamic rendering with Vulkan. I would also recommend you do the same, but that's a completely separate video. A render pass encapsulates any set of commands writing to an image or resource. It can be a compute shader writing to an image, you can build it onto an image, you can just draw to the swap chain image, whatever works, but we first need to encapsulate a resource. In my render graph, a resource is defined as anything that can be used by a render pass. So here's some code. Now what does this code actually mean? So first off, we're creating a structure called resource, obviously. This structure contains information on the type of resource, how the resource is accessed, how it's used, and the actual data, which should encapsulate most of the behavior we need. Of course, there can be any type of data, even though currently in this resource we only have images and buffers. In my render graph implementation, I actually allow for arbitrary data, which just passes extra info needed from the CPU. So how does the render pass take and handle these though? For simplicity's sake, I'll be leaving out some details here, but the render pass structure looks like this. A render pass has a name and a hash. The hash can be used for some optimization with the hash table, but for our purposes, it's not important. The name is used purely for debugging. We also see a pass type member though. What's that for? The pass type just tells us the queue we need to work on and how we need to work on it. For example, a graphics pass will be put on the graphics queue, a compute pass will go on the compute queue, etc. It also includes a dynamic array of resources, which is obvious. We need to keep track of our resources somehow. In Vulkan, I keep track of color attachments separately, but that's omitted to make this as relevant as possible to other graphics APIs. But then we also see a member that's a function pointer called callback. This is just the execution callback, which decides what commands are run and how resources are managed. Sounds super complicated and fancy, right? But it's literally just fancy terminology for a function that gets called when we execute the pass. Something extremely important though is locality. An execution callback should only be able to touch the resource that the render pass can. Hence why we make it take in the render pass itself and the current command buffer. Yay! You made it through all the boring prerequisites. Get ready for more. What is a directed acyclic graph? All render graphs are directed acyclic graphs, but what is that? A DAG, which we'll be calling it for short, has all these fancy words. Directed, meaning that there's a direction in the graph, and that's not all willy-nilly. With an undirected graph, you literally could not make a sensible render graph. All nodes of a render graph should usually lead to a single ending pass. Acyclic means that there are no cyclic dependencies, as a dependency cannot depend on a dependency that depends on that dependency. Sounds confusing? Here's another way to explain that. There's no path of nodes that starts and ends with the same node. I feel images make a much better understanding of this though, so here's a diagram I found helpful. This is a cyclic graph. We can get back to 1 by going 1, 2, 3, 4, 1. Simple. If this was acyclic though, 4 would connect to nothing or another node that wasn't 1, 2, or 3. Now, what we should know is that there's 2 to 3 types of render graphs depending on how you define type. We have a static render graphs, which only build once and cannot be changed. We have immediate mode render graphs, which are rebuilt every frame, and there's a mixed mode render graph, which only rebuilds when a change happens. Now there are pros and cons to each of them. For static render graph, we have the pros that they can be faster than an immediate mode render graph, and they can be as heavy as you want. But we have the extremely huge con that it's not flexible at all. For immediate mode, they're extremely flexible and lightweight, mainly because they have to. But the con is we have to spend precious time rebuilding every frame. And for the mixed one, it can be a bit heavier than an immediate mode render graph. It's flexible, but the main con is it's harder to implement. Now, me personally, I opted for an immediate mode render graph because it's flexible and when lightweight enough, doesn't have much impact on speed. Now, because you think of graphs, you might think we need a tree data structure, right? No, not at all actually, because we keep track of our resources. And we don't even need a tree data structure because we have all the information we need. And we just detect the edges and insert our pipeline barriers at the edges. Now we can finally fully dive into the code of a render graph. And I bring you yet another structure. This is so simple, we just keep our render passes and barriers. But how do we even end up filling these? There's many optimizations we can make to our graph while compiling it, like trimming dead passes, reordering passes, and merging passes. To trim dead passes, we can walk through our array of passes backwards and create a new array. And for any passes that don't contribute to the final image, don't add them to the array. But how do we determine what contributes to the final image? We can make the concept of a root pass and define it as any pass that has a right handle to a swap chain image. And we can then add all dependencies of this pass to a list. And if any other pass later down the line writes to one of those dependencies, upload its dependencies to the list and continue. Reordering passes allows us to decrease barriers. Now, why does decreasing barriers increase our performance? Well, we don't have any unnecessary wait times. We can do this by grouping similar tasks together. Like if pass A writes to resource X, then pass B reads from resource X, then pass C writes to resource Y, and pass D reads resource Y, we can reorder passes C after pass A, so we do both of our writes together, and the writes don't have to happen one after another. Merging passes further expands on this. If passes have enough overlap, we can just merge them using the multipass feature of Vulkan. I personally haven't implemented the merging passes optimization, nor have I seen someone implement it, so I wasn't able to really get into the specifics, but that should leave you with a good enough idea, and some of the resources in the description will have merging passes and how to do it listed. So now that we've built our render graph, how do we even run this thing? Well, this is actually the simple part. In our draw function, we just execute the graph. No, I'm just kidding. I'll show you how to execute the graph. For every pass, we run our pipeline barrier, if it exists, and then begin the render pass, run the callback, and then end our render pass. Very simple. Well, I guess that's it. That's most of how render graphs work. Of course, there's a lot more to this, and I will leave the main resource to actually help me understand render graphs and implement them in the description, along with my implementation of the render graph.